Okay, thank you.
But for the Fourier series, it's any periodic function, right? That can easily be broken down by derivatives to be brought, sorry, not broken down, by taking derivatives will result in just impulses. That's the idea, right?
Yes, sir. The thing was like I had gone through most of the homeworks already. I was just looking for some more problems to practice, I guess.
Let me see
So,
if I can find something online. Give me 1 second. Matter of fact, let me get the doc cam. Wait a second. I got to share the screen. We got 3 people. I sent that to everybody. I hope you all got it.
I think a lot of people have class during this time too. So
Oh, they do?
I think.
Okay. I've got, I had class earlier, had a Zoom meeting. I've been busy. You're in Auburn, right?
Yes, sir. Also, the poll came back, and 7 people are in Auburn, and 10 people are not.
Well, that's 17. We have 26 students.
Yeah.
I'll try to tell Burgess that. Can you send me that in an email? I'll just forward it
Okay.
to Burgess. He wants that kind of information. All right. Let me. Are you seeing you're seeing a second screen, right?
I'm seeing a black screen right now. I'm not seeing.
Are you seeing my? Is it now say launching Zoom in? You see that?
Kind of off in a corner, but not really on the screen. So.
Hold on. Let me.
Oh, there it is. It just disappeared.
What are you seeing right now?
I'm seeing your face.
Just me. All right.
Yes, sir.
Let me share the screen. All right. Now you're seeing something that says launching, sort of.
Sir.
Okay, good. Now let me see if I can get this doc cam working. It's frozen.
Okay, I sent you an email with the results of the poll.
Okay. Let me restart this thing. It's got a problem. Is Nick there too?
Yes.
Oh, there it is.
Yes, I am.
All right. So what you wanted to do is you're asking for examples. I might be able to find some online. The problem, I haven't really looked. It's fairly straightforward. Wait a second. It's fairly straightforward to do most of these. Just look online, see what's available. MIT doesn't get much better than that. That'd be a good one, but it's a straightforward one.
Okay.
First derivative. What else does MIT have to offer? How about if I just,
That one seems good.
I'll just send you everybody the, why don't I just, wait a second. I can do this in the chat, can't I? Where's my chat? Don't I have a chat? Chat. There we go. I got a chat. Now, here is the MIT And you can share that in GroupMe to everybody too.
Okay.
Let me just take a look at these problems because I mean, MIT is, when it comes to schools and engineering, they're probably the best, or one of the best. All right, we can talk about these without even doing. First one right here, it's periodic, its period is 10.
Yes, sir.
After that, so omega naught would be 2 pi over 10. The next thing I'm going to say is that for this particular thing, if it's periodic, goes on forever. If I take one derivative, I get a delta of t minus delta of t minus 1, right? We could easily get the coefficients. Do you agree? The coefficient would be what? It would be 1 over t, or 1 over 10, times quantity, well, 1, because the first delta function is at 0, and then be 1 minus e to the minus j, and then it would be omega naught 1, right? Then you'd have to divide that by j n omega naught to get c of n, then you've got it. But he does it right here for you.
Okay.
All right, you can check your answer here. Don't worry about that. This is got what? When you take derivatives, you're going to get 1, 2, 3, 4 delta functions. Right?
Yes, sir.
This is just one derivative. It's straightforward too. I don't think that one's very hard. This one, you take one derivative, you get what? A constant from 0 to 1. Then it goes to 0. Then another constant, only it's negative from 2 to 3, right?
Yes, sir.
You'd have to take a second derivative of that, and then you would get 1, 2, 3, 4 delta functions. I think this one's straightforward for you, really.
Could we work it out?
Yeah.
If it's okay with you?
Sure, why not? I don't know if I can cut and paste this, but I might be able to. Let me just see if I can. I'm going to try to do it here. So here it is. I can do this on the paper, but I think this one's so simple. We can do it right here. If x of t, then a derivative of this, right, would be let me see. Derivative would be maybe it would be easier using Docam, but you can see the function. For this one, the derivative goes to 10, right? So try to pull that out over here to this side so I can see it. Oh. All right, so the first derivative is going to be, just put x prime there, it's going to be a constant, and it goes from 0 to 1 over over a 1, so it's
Mhm.
1. Then from 1 to 2, it's 0. All right. And then
Yes,
from
sir.
2 to 3, it's -1. Do you agree with that?
Yes, sir. So it will be 4 pulses,
4 deltas.
4 deltas, sorry.
Right. And then we have x double prime, right? And now we're going to have this height of 1. At 1, it goes to -1. At 2, it goes to a -1, right? And then at 3, it goes to +1, right?
Yes, sir.
Do we have 4 people or are there more?
3 students
Yeah,
and you.
plus me. So there's not a lot of people here. And I did send that invite to everybody, I think. Right?
Pretty sure you did, yeah.
Okay. Well, if this is it, remember that's the double prime. So C of n double prime would be 1 over t. And t for this one's still 10. Times the integral of x double prime, right? E to the minus j n omega naught t dt. And you might as well go from -1 to 9. How's that? That's over a range of a period, but it's slightly less than the first delta, right?
Mhm.
Okay, everybody? All right. So what's it going to be? That's 1 over 10, right? Well, the first delta starts at 0, so it's going to be 1. E to the j n omega naught times 0 is 1. Then you're going to have what? Minus e to the minus j n, right? Omega naught times 1, or just omega naught, correct?
Yeah.
That's going to be, that occurs at 1. It's got a minus sense to it. The next one's got a minus sense. Where does it occur?
Can you bring the paper up a little bit?
Oh, yeah, thank you. Yell at me
Thanks.
about that. I'm bad about that. And I'm trying to change the magnification on this, but I don't see this here. See, here's this where it has zoom in and zoom out. It does not change the magnification. What I'm trying to do is change that magnification. And I don't know if I can do it there or not. You would think that that thing would be right on the screen, but what is this? Mm-mm. Let's see what this says. It's got auto for zoom. Hey, wait. Surely there's a way. I'll have to play with this later. Anyway, there'll be a 2 here, right? 2 omega naught.
Yes, sir.
And then finally, what's the last one?
Minus e to the minus j n omega naught 3.
Times 3. All right. Now, omega naught is equal to 2 pi over t, or over 10, or it's pi over 5, right?
Mhm.
Now, you can plug that in there if you'd like. And there's going to be a way we could easily turn these into a trigonometric function if we want. So we have 1 over 10. And then we're going to have 1 minus, just look at this. If I take a look at these, you can see that there is a progression of what? E to the j of just j omega naught times these things, right?
Mhm.
Follow me on what I'm about to do. We'll see if this works. If I have e to the minus j and omega naught over 2 taken out of this first one, I get e to the j and omega naught over 2 minus e to the minus j and omega naught over 2, correct?
Yes,
That's these two. Now take a look at this too. I'm going to have, I'm going to just take out a e to the plus j and omega naught over 2 out of there. Make it, if you add this exponent and this exponent, you're going to get minus n 5 omega naught. And if you divide that by 2, it's 2.5. So what I'm going to do is take a e to the minus j omega naught, and it's going to be 5/2 out of there. And if I do that, you'll see 5/2 out of this one will leave me as e to the minus j n omega naught over 2. And then this is going to be minus e to the minus j, or plus j n omega naught over 2. You follow me? Just take a look at the first one. I factored out j n omega naught over 2, and I'm left with this, right? These are these two.
Yes. Okay, that makes
Next
sense.
part, what I always do is I add the exponents and divide by 2, and I factor that out. So I'm factoring out e to the minus j omega naught 5/2. That leaves me, the back one here is e to the minus j omega naught over 2. That would be 6/2 or 3, right?
Yes.
This time, and then this, remember, this has to be 4/2. So plus 1/2 minus 5/2 is 4 minus 4/2, right?
Mhm.
That's 2. That's this one. So what does this turn into? That's 1 over 10, right? Then we have e to the minus j n omega naught over 2 here. And this is going to become what? 2j times the sine of n omega naught over 2, right?
Yes.
What about the next part here? This is going to be plus, actually it's what? It's going to be minus, and I'll put e to the minus j and omega naught 5/2 out in front. And this is going to be minus, right? That's minus the 2j, right? Times the sine of omega naught n over 2, right?
Mhm.
Now, you can see I can factor out the 2j sine of omega n omega naught over 2. I can factor that out in front, and I have
The paper needs to come up a little bit.
like that.
There we go.
N omega naught over 2 divide by 10, right? Now I'm left with, I took the 2j out in front, I have e to the minus j n omega naught over 2 here. And it's going to be minus e to the minus j and omega naught 5/2, right?
Yes.
All right, now you can do this again. This is getting a little, I can easily see here, if I add this and this, I get 3, right? 3
Yeah.
minus n omega naught times 3 over 2, correct? Or I'm sorry, 3, just 3. It would be 6/2, correct?
Yeah.
Yes.
All right, take that by 2, that's going to be 3/2. So now if we just work on this one and we take e to the minus j n omega naught times 3/2 out, I'm factoring it out, okay? Are you with me?
Yes.
Now, the reason I'm doing it, add the exponents, divide by 2. Now when I do that, what am I left with? Well, here I would have e to the j n omega naught, wouldn't I?
Yes.
And what would I be left with here? I would be e to the minus j n omega naught, right? Yeah. Right?
Yes.
All right, what is this?
That's another sign.
2j, right?
Mhm.
Times sine of n omega naught, right? And that's just a phase term. So this is 2j, first one, times sine of n omega naught over 2 over 10. Then the second one times 2j times the sine, and this is just n omega naught, right? And then there's still this e to the minus j and omega naught over omega naught times 3/2, correct?
Yes.
Hmm?
Yes.
All right, j times j is -1, so that becomes -1. 2 times 2 is 4, right? 4 divided by 10 is 2 divided by 5. So this is going to be minus 2/5 out in front. I'm just leaving it like that. Okay.
Mhm.
And that's your answer in a closed form. Now, what is omega naught? Omega naught is 2 pi over 10, or
Dr. Baginski,
I know.
question. At some point, didn't we have to divide by j and omega naught squared?
We're going to, but this is
Okay.
still C. We can actually, when I leave the J and the J's there, I put a minus sign there, but we're getting the C of n prime, double prime, pardon me, right?
Okay.
You're absolutely right. As a matter of fact, what I can do is just take this, right. It's kind of messy, but if I take that right there and to the next page, if you just divide this by j and omega naught squared, the j's will cancel, all right?
Mhm.
They'll cancel. Remember, we had 2j times the sign and then another 2j. So then you're going to divide by j and omega naught squared. So the j's you'll get rid of those. You're left with the n omega naughts downstairs. And I'll tell you, I'm spending a lot of time on this, but when you condense it all down, the key thing is the sign and the sign behavior here.
Right. Okay.
And omega naught is 2 pi over 10. So this would be pi over 10 would be omega naught here. And this would be pi over 5.
Okay.
It is messy, but I think you see what I'm doing, right?
That's it.
All right, now MIT probably is going to have an answer that's in a different, slightly different form. We can take a look. They still have it in kind of a wacky form too.
Mhm.
But they do have the two signs, and that's what we had, right?
Yes, sir.
It'll work out. It'll
Okay.
be the same. Let's see what else he's got.
Is this MIT document, is it using K as N?
Yeah, and that's
Okay.
fine, because in the frequency domain, most of the time they use K. And the time, like if it was sampled in time, they'd use N.
Okay.
It doesn't matter.
All right.
Then he wants inverse Fourier series. I'm not worried about that, the inverse stuff.
Dr. Baginski, also, I feel like after that problem, I feel like I have a pretty good grasp on Fourier series. Is it okay if we could do like a circuit problem?
Yeah, which one you got in mind?
Maybe like, I wouldn't say an RLC where you have to combine an impedance.
Think
Possible.
about which one you want me to do, and I'll be back in a second. I'm getting some tea. All right?
Okay. Guys, thoughts, opinions?
I think an RLC is a good option. I don't have any in particular offhand.
Like, I think like doing one that we haven't seen before would be good, but I don't know how to phrase it, like make up a problem. So
I mean, you could like draw it out and then take a picture and email it.
like this? No, that doesn't work.
If you take off your background, it would.
That's true. It doesn't have well, the problem is like I can't minimize while recording. So
Ah,
I
that's
can't
problematic.
change it, which is an issue.
Do you want me to draw something out and then I can
Sure,
email it to him?
that would be great.
Okay. What are you thinking?
Something that has RLC and maybe something in parallel as well. Maybe
Okay.
like an R and a L on the top in
Mm-hmm.
parallel with like an R and a C.
So an RL in parallel with an RC?
Yes.
Okay, that's it?
Or
Nothing in
like,
series to start with?
well, okay, hold on. How about an R and a C in series to begin with?
Mm-hmm.
And then like in parallel with an R and a L, possibly, and make everything one.
What is in parallel? The R and the L?
Okay. How about if I draw one out? I'll just send a picture to you, and then you can just,
Okay,
either way, I can just email it. It's
yeah,
not a big
that's
deal.
fine. All right, I'll be right back.
Making how you will be making up feeling close. I'm really happy.
Okay, which one did you have in mind?
I think like what we decided on was like we're going to draw one and then send it to you. And
Just share your screen. You can share your screen.
I don't think I could draw it on the screen,
Mm-mm.
but
Don't you have, do you have you have a piece of paper you're drawing it on, right?
yes, sir.
And that camera that is looking at you, you could take that paper and put it right in front of it, right?
The problem is like I can't really minimize while recording. Or let me see if I can just hold on.
Just take your paper like this.
The problem is like the virtual background sees it as white and it
Oh.
says it's the virtual background. Like
Well, you go ahead and see what you can do. If maybe I can draw it for you. Can you see what I'm about to do? How do you want the first element to be what?
hold on. Okay. Is this better? Wait. Dr. Baginski, can you see this?
What?
Dr. Baginski, can you see my screen?
You got looks like a resistor, an inductor, and then a capacitor in parallel or something. All right, so tell me, I'm gonna go ahead and try to draw this. The first thing is you got a source here, VS, right?
Yes, sir.
Then you had, is it an inductor in the next?
Yes, sir.
An inductor, and then a resistor?
Yes, sir.
All right, and let's call this L and this R1. Then over here, what do you have?
A capacitor.
Capacitor, call that C, and?
Another inductor.
All right, so you got L1 and L2 then, right?
Yes, sir.
And what did you need out of this? Is this the output voltage here?
Find the current over L.
Which L?
L2.
So you want I here, right?
Yes.
So really your transfer function is I2 over VS.
Yes, sir.
All right. You can do it a couple of ways. Obviously, you can use nodal if you want. You can use nodal analysis for this one. Let's put in the impedances. This is SL1. This is 1 over SC, right?
Mm-hmm.
And this is going to be, call this SL2, right?
Yes, sir.
Now, if we look at this, really, if we want the current here, we could get the voltage here and then divide by the impedance, right? By the impedance of the inductor.
Mm-hmm.
All right, what's this voltage going to be here? Here's what I'm going to do. I'm going to call ZLC equal to the parallel combination of these two, which is 1 over SC plus 1 over L2S, right?
Yes, sir.
And then if I go ahead and multiply top and bottom by S and then divide by C, so I have, I'll first multiply by S, and then I have S squared here times C plus 1 over L2. Now I know there's a C there, so now I'll divide everything by C. All right, and I'll call that ZLC. Do you agree with that?
Yes.
Nick, can you see it?
I can see it. I'm with you.
Jordan? So Kihan, can you see this?
Dr. Baginski, can you go up a little bit? Okay. Okay, thank you.
Sure. Was so, this bothers me. I can't see everybody. It doesn't automatically show everybody. Okay. Sokihan, I don't know how to pronounce your name, but can you see this okay?
He said something in the chat, and he can
I
see it.
see, okay. I'm going to ask for everybody to turn on their cameras during the exam on Wednesday. Do you mind trying to turn them on now? We're talking about a virtual exam, so if you have, can you try at least? I want to see what kind of a problem we run into when we get a lot of people talking or interacting.
Dr. Baginski,
Your
what if,
computer.
yeah, what if our computers doesn't have a camera?
Well, that's, the whole thing they tell you to do is make sure everybody has a camera so you can see them. And I'm thinking, all right, I can ask that. I can't force anybody. We'll do the best we can with what we got. Can you turn on your cameras if you have them, please? I mean, if you're unshaven and unbathed, just deal with it. I can handle it. I mean, half the time I'm watching people in their pajamas and stuff these days when we're in meetings. They aren't going to get cleaned up for any of this. You got a camera or not, Nick?
I have one, but it's kind of iffy.
That's all right. Iffy is better than nothing. Spencer? No?
Chris said something in the chat.
My computer does not have a camera. Okay. Well, if you can try to turn your camera on, I'd appreciate it. I'm just trying to get a feel for if we get a data crunch or if this thing starts dropping out, because it's happened in some larger meetings I was in.
Dr. Baginski, in my thermo class, we had like 50 or 60 people taking the test, and most of them had their cameras on, and it worked pretty well.
This is in Zoom?
This was through Zoom. So
Okay.
I think Zoom can handle it. It's just...
It can handle it in terms of the network available to Auburn University at their end, but the problem is people, especially in remote areas that have different types of, they have like DSL or some lower rate, what you'll see is them literally freeze and fall out all the time. That's the reason I can't give an exam where it would be one problem at a time. You get 10 minutes because some people will not be able to see it. I got one person with a camera. That's you, Lydia. Nicholas, do you have a camera or not? Just try to turn it on. All right, I'm going to get back to this problem. Here's what I'm going to do with this problem. First thing I'm going to do is find out what V out is right here. That's going to be the output voltage across the R and the C, right? So that value, V out, right there, would be equal to Vs, right? Times what? Times this Z of LC over Z of LC plus SL1 plus R1. Do you agree with me?
Yes.
Okay. Now V of S can be, this is called the input voltage as a function of S. It can be anything, it doesn't matter. Now, once I have that, then I divide that by SL to get the current. Do you agree?
Mm-hmm.
So now I say that the current I of S that you want through the inductor would be this, V input of S times ZLC over ZLC plus SL1 plus R1, and then divided by SL1. Agreed?
Yes.
All right, now, If you look here and just start to substitute, let's let VI of S be out here. Well, this ZLC is this right here, right?
Mhm.
You'll notice there's an S here and an S here that will cancel. So I'm left with what? I'm left with 1 over, and this is going to be L1, or I'm sorry, this is L2, pardon me. L2, that should be L2. L2 times C on top. And then I have this. Well, this is equal to this. So I have S over C, S squared plus 1 over L2C. That's the first term that goes right here, plus SL1, right? Plus R, R1. Do you agree?
Mhm.
Now it boils down to simplifying. If you can see right now, I'm probably going to multiply by everything by S squared plus 1 over
Dr.
L2.
Baginski, could you shift the page up a little bit?
Yeah,
Thank
I
you.
will. Let me get this out of the way because it sort of hampers things. So now what I can do is this. I'm down to the point where I've included the value of ZLC in here. And even though it's a little messy, I can see my next step would be multiplying everything by this, right? Because that's still a fraction, right? In the denominator. When I multiply everything by that, I'd have SC downstairs, then I'd have SL1 times S squared plus 1 over LC here times that, plus there would be S squared plus 1 over LC times R1, and then this would occur up here, correct?
Yes.
And then you have to tell me what V of S is if you want an actual current value. This would be the transfer function, really. If
Okay.
I took the actual V of S and brought it over here, I'd have the transfer function, wouldn't I?
Mhm.
And I mean, that's how you would do it. And then from there, just go to partial fractions.
Okay.
Is this an actual problem somewhere?
No, there's some problems that are very similar to this.
But that's essentially how you do it. And I'll tell you, the problem with a lot of these is people get tripped up. They aren't careful when they do the actual manipulations here. They'll forget things or add things, and that's where the whole problem gets bad in a hurry.
Okay. Could you possibly do a duality problem?
Yeah. Tell me one, and I'll do it.
Let me look through the homework.
You know, I think that the MIT website has tons of problems on it. They have there's a guy named Oppenheim that has done a lot of this, and there's 3 or 4 other people. And I mean, they've got loads of problems in both their circuits courses and their signals and systems for Laplace transform type problems. We got 2. How many people we got? 1, 2, 4, 6 people. Did anybody else have any other questions? Well, she's coming up with one for duality.
Yeah, I had a block diagram question, but I need to find it though.
Jordan, do you have a camera?
I do, but I would have to like restart my computer.
Don't bother. Don't bother.
Yeah. But I do have one now.
Could you possibly do homework? Wait, no, that isn't duality.
Are your other courses going okay?
So far.
At least turn your audio on, so I mean the other people there, so I can, if you want to comment, you can make it like a class setting, if possible.
This isn't duality, but it is one of the homework problems that you gave. I think it was 5 point, let's see.
Can you just tell me what it is? So
Okay, I'm trying to grab my book right now.
it's 5, did you say?
There's several of them. They're all in a general section together.
5A or 5B?
Aha. 5.45. It isn't a duality problem, but it is like you have a waveform and then you apply Fourier transforms to it.
Well, is it in the book 5.45?
Yes, sir.
I don't know what homework that is. Do you know the number of the homework?
It is homework number 16.
Okay, which one?
5.45. If you scroll all the way down to the bottom, there's a whole list of PDFs.
Yeah, this one.
Yes, sir.
What do you want for this one?
It asks for express the Fourier transform.
Mm-hmm.
So if we're given a waveform, like how would we apply that and make it into a Fourier transform? Is just
Yeah, for Fourier transform, this particular one is going to be, let's see. You could do it with derivatives, even though typically you don't, but if you have X, I'm going to go to the document cam now, and I'm going to pull this over here so I can see it, and let me get the document camera. So what I'm going to try to tell you is what properties I use. I know that I have X of t going to X of omega, right? Then if I have dx dt of t, that would go to j omega x of omega, right? Correct?
Yes, sir.
And I know that if I had the integral of x of t from, I guess, minus infinity to t, and this would be x d tau. I'm trying to think of where that is in your book. Hold on. Because I'm not sure in your book what properties they actually have listed. I'm used to a different book. Yeah, this is property 8 on page 229. And when we do the integral of that, you're going to get an x of omega, right, divided by j omega. And then it's going to be add to that pi times the x of 0 times delta of omega. And here x of 0 is simply the integral from minus infinity to infinity of x of t dt. Now, that's what you get, and there's a reason I'm doing this. I'm going to say this. If I take a look at this function right here, that's right there, right? What happens if I take one derivative of that? Just
they would get like a pulse.
We want f of t goes to f of omega. This is our goal. We want this. Now, if we take one derivative of that, df of t dt, what does it actually look like?
It would be a negative pulse and then goes to 0. And then, or
from minus 2t to
a delta up.
Minus t, it becomes a constant value that would be minus a over t, right?
Yes, sir.
0, right?
And then like a delta up, I believe.
No, it stays 0, right? Take a derivative.
At 0?
What? Oh, I'm sorry. You're absolutely right. This is going to be 2a right here. My bad, right? Sorry. And then it's going to do what?
It's going to be at 0, and then it's going to have a go up from, I'm not exactly sure of the bounds, but it's similar to your
look.
negative only in the
Look,
positive.
it goes, it's negative here, right?
Oh,
0.
right.
Then
It goes up,
2a, right?
negative slope.
And then negative again, right?
Okay.
All right, take a look. So it goes up with 2a, then it goes minus a over t, right? Again, and this would be at t and 2t, I believe, correct?
Yes, sir.
I gotta take a look at that. Yeah. All right. Now that's the derivative, right?
Mhm.
What's the transform of that? Well, pretty sure that you can know where a delta function goes to. That's in time. That would go to what? Just 2a, right?
Mhm.
2a, right? And it's a constant, correct?
Yes, sir.
Now, what about these two? Well, what does this look like? You could do it a few ways. This looks like a shifted pulse, right? This is a shifted pulse. What else does it look like? There should be something that comes to mind.
2 U of t's.
It also looks like what? A pulse waveform centered about 0.
Oh, and then you have another
Modu-
pulse added to it. And
Well, modulated with it. Here, we can do it this way though. If we had this right here, do you agree that first of all, you all see a way to describe this? This would be what? P of width t of omega plus t times 3/2, right? And it would be a minus value there, and there'd be minus a over t as a coefficient. Do you agree with that? What about this one? It would be minus a over t times p of t omega minus t times 3/2, right?
Dr. Baginski, could you shift the paper up a bit?
Yeah. But you see what I'm up to. Huh?
Yes, sir.
All right, now, we could do these transforms. A matter of fact, I think I did this a couple of times. I showed you about a right shift in frequency, with duality being a left shift in time, if we're going to use duality. And we've done this. I'm going to do one of these, but I'm going to tell you what this is going to come down to. It's going to coalesce into a cosine waveform times something. That I promise you. Now, I know a pulse in time. Let me do it this way. And I hope I'm answering your questions, but work with me on this. If I have p tau of t, just that, we know that's tau times the sinc of omega tau over 2, correct?
Yes, sir.
By the way, can everybody else see this?
Yes.
Can you give me some indication of life? A thumbs up or thumbs down or whatever? Got 1, okay, 2. I heard somebody, Spencer.
Yep.
And so Keith, I don't know if you guys, there should be emotions available to you on that. You should be able to put a thumbs up or applaud. Or maybe there's a boo button somewhere that I don't know. But anyway, we have that and we come down to what? That's tau, right?
Yes.
That's the sinc. Now it's going to be t tau over 2, right?
Mhm.
Over here, this becomes 2 pi, right? Then we're going to have p tau of minus omega, correct? We might as well leave it as plus omega and just divide this by 2 pi. Now, the reason I did that, I'm saying that a pulse function right here goes to this in time. But if we have a pulse weighted by 1 in frequency, another a window of width tau in the frequency, the time domain signature that would cause that would be that, correct? What's the one thing about this? This is striking and troubling. Is it causal or non-causal? Isn't this on forever?
Yes.
Now, what does that really mean? If I had an impulse response, right, if that would be p tau of omega, which is my h of omega, right? What happens if I put a delta t in here? What do I get out?
Um,
The impulse response, isn't this h of t?
yes.
All right, what's the troubling part about that? Does this have any non-zero values for t less than 0?
No.
It starts at t equals 0 is when it occurs, right?
Yes.
But this thing's been on forever, hasn't it?
So it just doesn't line up correctly? It's
No, it's called non-causal. You can't have a real-time filter, something that's taking real data and then outputting data. They always check it with a delta function that has data that's starting from t equal minus infinity because it would anticipate this thing. This is non-causal is what I'm trying to say. Everybody?
I'm with you. That makes sense.
I'm just trying to say that if this is an actual filter, you cannot build a filter that does real-time processing and tells you that something's anticipating this is going to occur. You can't. That's a non-causal. It doesn't, causal means the output is caused by the input. Well, even when the input isn't there, it's still got an output going and it's non-zero, and that's impossible. That should make sense intuitively to you. Okay, now, having said that, getting back to this, now I know the relationship between this and this, right?
yes.
Keep watching. Keep watching. Now, what about when I have x of t, any x of t times cosine of omega naught t? What happens out here? It's 1/2, right? X of omega plus omega naught plus x of omega minus omega naught, right?
And that's X, like capital X.
Oh, that's right, capital X, right? All right, let's try it. If I have tau over 2 pi times the sinc of t tau over 2 times cosine of omega naught t, doesn't that go to, and I'll put it down here, 1/2 times, well, we knew what this goes to. That's a pulse function, right?
Yes.
Of width tau. That would go to what? A pulse function of width tau centered at omega plus omega naught, right?
Mm-hmm.
Plus a pulse function with tau centered at omega minus omega naught, right?
Mm-hmm.
Now think about the actual function we had. We had two functions.
Oh.
Right?
Mm-hmm.
This middle point is 3t over 2. Wait a second, is this frequency? Oh, that's time domain, sorry. I thought this is frequency. My bad, this is even easier. I'm sorry, this is a frequency domain problem. I didn't look at the axis. I thought this was in the frequency domain. This is even true, but it's worth doing. So anyway, if you had this in the frequency domain with 2a here, then you could get back to the time domain. This 2a just goes to 2a times delta of t, right? And these two transform back as this, where omega naught here would be 3t over 2.
Okay.
This is the modulation property. It's easy to get to. It's a good problem, though. Now, if you, getting back to the original one, and I'm so sorry I spent some time on that. I need to clean my glasses so I can see this. That's an f of t, not an f of omega. So now we don't need duality with this one. We can go right to it, right? We know if f of t goes to capital F of omega, right?
Yes, sir.
And we know that if we have, and I'll tell you what I'm doing here. I'm going to take the derivative of that function first. So I'm going to have f prime of t, and f prime of t is exactly what we were talking about. Sorry, I got sidetracked here. This is t, 2t, minus t, minus 2t. And the derivative was this. This is minus 2a over, or I'm sorry, it's minus a over t, right? That was ours, right? Now that's an f prime of t. First, if I have that, can I easily get the f of omega of that?
Yeah.
Yeah, just describe what they are. Well, what is this?
It's a
This is,
pulse.
minus a over t, right? A pulse of width t at t plus 3/2 cap t, right?
Yes, sir.
What's this one? Minus a over t, p tau of t plus or minus 3/2 t, right?
Yes, sir.
Okay. What's the transform of this into the frequency domain?
Sync.
Well, you know, the p tau of t would be equal to tau times the sync, right, of omega tau over 2, correct?
Yes, times E.
And well, I'm going to put the minus a over t right there, right?
Yes, sir.
Now, tau is t. We'll get to that in a second. But it's shifted by that. So it's multiplied. This whole thing is multiplied e to the j, right, times 3/2. What? It's shifted by 3t, right?
Yes, sir.
T times omega, right?
Yes, sir.
You all see that right there? That's what this pulse will go to. Now you'll notice because the width is t, tau is t, these two cancel, right? And you can put a cap t in there if you want. And then that's fine right there. Now what's this one going to be, the second one?
It's going to be the same thing except for
Except?
the E, the negative. It will be a negative E.
Right,
E to the negative
3t omega, right?
Yes, sir.
Minus a, and it's just going to be minus a times the sync, right? Of omega t over 2, correct?
Yes, sir.
That's the transform of the derivative, correct? And then you got to have plus 1. You got the 2a there, right? You have 2a in the time domain would go to what? Sorry. Yeah, that's a delta function, 2a delta of, 2a delta of t, right? When we take a derivative.
Mm-hmm.
Can you see how you take a derivative of this thing? This is when you brought it up. You take a derivative, it goes from a to plus, minus a to plus a, that's 2a by a delta of t, right? Slope is infinite. So it's going to be the 2a delta of t transforms to what? Just 2a, correct?
Yes, sir.
All right, and that's the transform. Now watch one thing you can do to clean it up. Look at these coefficients. Couldn't you factor out the minus a, right? Sync of omega tau over 2, and then,
Would that make it into like a sine
cosine.
or cosine? Okay.
It would be 2 cosine of 3t over omega. You see that? And that is what? That would be the transform of the derivative, right? So if we wanted the actual function, we would want what? We'd want the integration of that. And with integration, we just did that. That's in your book. But if we wanted, now we take that, we want to know what the transform of the integral of that would be. And that is on page 229, table 8. And that means we take x of omega over j of omega. Now, I'm just going to tell you, this we can clean up if you want. But you're going to have, I'll try to do it here. You're going to have minus a times 2 cosine, minus a times 2 cosine of omega cap t over 2. And then you're going, I'm sorry. Three halves t omega. So there's a 3 here, 2, minus 2, and then it's going to be times the sync of omega t over 2. And it's plus 2a. And that is the derivative, right?
Yes, sir.
I mean, that's the transform of the derivative. So now, according to the theorem, I have to take that and divide it by j omega, and this is on 8, by the way. And then I have to take that, remember, this has to be divided by j omega 2. And then I have to take x of 0. I have to find that out. So just bear with me. So I have to integrate from minus infinity to infinity, simply x of t dt. this is equal to x of 0. It's when omega equals 0. And you take a look at the waveform. Here, you guys can do this one. What's the integral of this from minus infinity to infinity by the inspection? Class?
0.
Yeah, that's my point. It's 0 just by inspection. So if it's 0, then you can forget about the second part of that, where you have pi x of omega times delta omega. The only thing you're going to do is take this and divide by j omega. And this, in fact, would be the true x of omega of that. Now, how did he put the answer?
A little bit differently.
What he did was, when he did this, he's going to get a sinc out of here. I'm going to try to explain this. His results will be mathematically identical to ours, but you see how he's got these omegas here, right? He's got 2. Remember, we had -2. Actually, we had 2a, I think, didn't we? It's 2a divided, he's got a plus j on top. So if that goes down, it would be 2a divided by j omega. Do you see this right here?
Mm-hmm.
All right, that's exactly what I have. If you look at my dot cam right here, I have 2a divided by j omega, and this is the same thing he has, only in a different form. Because in sinc, instead of the sinc here, he puts sine of omega t over 2 divided by omega t over 2. And I'm not sure that's the best thing for him to do, but he got this. Oops. Let me redo that. Where is this? Where'd that thing go? This is. Well, I'm not sure what happened, but you know what I'm doing, don't you, class? Okay, that's how you do that. That's a good problem. Anything else for the good of the group?
I only have 15 more minutes till my next class. So if someone wants to record after me,
Well, I'm going to have to get off of here too, because I've got stuff I have to attend to. I'm doing my best, but I've got another course and we've got meetings coming up this afternoon that are, matter of fact, we've got a faculty, it's a general faculty meeting, and that is at, when is that coming up? It's coming up at 3:30, and I got to run up to a doctor's office and pick up a script. Let me see what I got here. Hang on for 1 second. Oh my goodness. And I've got a bunch of emails. It's amazing how many emails you get I thought I used to get a lot of emails. Make sure if you're sending me one, you put down like in the subject, 2120 test or something like that, because I got to try to differentiate you guys from the rest of the world.
okay. So Chris asked a question in the chat if it would be possible to write on an iPad with a stylus.
Yeah, as long as the final form of the document is put into a Word format and then uploaded, all right?
Does it have to be Word, or could it be PDF?
I would prefer Word because I can easily edit that. I can make comments when I'm grading. PDFs are a little harder for the stuff I have. What I'm trying to do is this. I'm trying to make it easy so you will understand when I grade it, I'm grading it.
Okay. He also asks if he can use his phone during the test for a camera.
Yeah, for a camera, sure. You're going to have to. This has been an experience for me too. I've taught distance courses, but they had somebody record them, and literally the tests, when they administered to them, you had a proctor that was that would watch over you, somebody that's effectively a person you could trust, like for instance, an Auburn graduate's now the division head or something like that. But we can't do that here. So we'll do the best we can, and it'll be on Wednesday, okay? Any other questions? Because I'm going to have to get going too.
Okay.
I don't think so.
So one last question. So when you send out the emails, it will be 15 minutes before class, right?
It probably might be as much as 30 minutes before.
15,
Class starts at
30.
10. My
Oh.
meeting is done at 9:30 typically with my this president's cabinet, and I'll send it right after that.
Okay. So will the Canvas page be up during this time, or?
Yep.
Okay. And
Uh-huh.
and it will be submitted 15 minutes. It can be submitted 15 minutes after class.
That's right.
Okay.
That's right. And I'm going to ask everybody on the honor system to not communicate with each other and to not use the computer for anything, even though at one time I was going to let you do it. But then the problems would be so hard. It would be almost it'd be something that I don't know if anybody would get them. What it's going to amount to, you can use your book and your notes. And that's it. Okay.
Okay. That sounds good. Thank you.
And if there are more questions, I'll try to get to them after 5 today, okay? Okay. And I don't know how many people weren't available, but hopefully this covered enough material. So
Yeah, this video should be up in like an hour, hopefully an hour or two. So.
okay. All right. Well, with that in mind, I've been at this since 9 this morning, and I'm ready to get off it. So take care. All right.
All right. Thank you.
Take care. Bye-bye.